I'm starting a video on heat transfer, and as you would have studied in some earlier classes, and the three modes of heat transfer: conduction, convection, and radiation. Here we'll be discussing heat transfer through conduction, and we will be looking at what do we mean when we say the word steady state, and we'll also look at the term coefficient of thermal conductivity. So let us say we have a metal rod. And we say heating this end of the rod. Let us call this end A, and this is end B, and we're giving heat Q over here. So this end gets heated up, and as you know, heat transfer in conduction happens from particle to particle. So the first particle over here will get heated up. It will pass on the heat to the particle next to it, and that in turn will pass on the heat to the next particle, and the process goes on till the entire rod gets heated up. That's how heat gets transferred in the process of conduction. And conduction is the process of heat transfer which generally happens in solids. So let us look at this process in more detail. What happens is, if I look at one particular cross section, let us say I'm focusing my attention on this cross section of the rod, and this would comprise of number of particles of this particular metal. So when heat reaches this particular surface, three things happen. One is heat is absorbed by the surface, heat is transmitted by the surface, and heat is lost through the sides. Or simply saying, heat is lost, right? So let me explain this. So heat has reached this particular surface, so some amount of heat will be absorbed by this surface. Let us call this cross section XY. The XY will absorb some amount of heat. Some of the heat will be transmitted to the next cross section, X1, Y1 probably, and some amount of heat will be lost through the sides or from the periphery of that particular rod. So these three things happen, and therefore what happens is the temperature of this surface is not constant. Similarly, same thing happens over here. Let us call this cross section X1, Y1. It will absorb some amount of heat, it will transmit some amount of heat, and it will lose some heat through the sides. Now, as far as the absorption of heat is concerned, that continues for some time, but after a certain interval of time, the heat absorption stops. Meaning that if I'm looking at this cross section, it has absorbed some amount of heat, it has attained a certain temperature, and then it stops absorbing heat. And this process happens on all cross sections one by one. So first, this cross section will reach a state of what I may call as a state of saturation in terms of heat absorption. So it has absorbed a certain amount of heat, it has reached a saturation level, and it is not absorbing any further amount of heat. Therefore its temperature becomes steady. Same thing will happen to this cross section afterwards, and later on this cross section and this cross section. So what happens is all the cross sections reach a certain temperature, and the temperature remains constant. When I say temperature remains constant, it means I don't mean that all the cross sections will attain the same temperature. The temperature of cross section XY could be, say, 70 degrees Celsius, and as we go in this direction the temperature will decrease, but XY will remain continuously at 70 degrees Celsius. This may remain continuously at 65 degrees Celsius probably, and this cross section may be at 54 degrees Celsius, but the temperature will not rise. Whatever heat that it receives, it doesn't absorb, it transmits, or it is lost. And when that state is achieved, we say the rod is in a steady state. So steady state means all the cross sections have attained saturation, they can no more absorb heat, and therefore the temperature remains constant. The temperature of each cross section will be different, but it will remain constant, and therefore we say it has reached a steady state. One of the features of steady state is that there is no absorption. So whatever amount of heat reaches this is immediately transferred. And if I'm able to insulate this rod, so there are no losses. There's no losses because it has reached steady state. There is no absorption. So the only process that happens is transmission. So if it receives heat Q, it immediately transfers heat Q to the next cross section, and this cross section would immediately transfer heat Q to the next cross section, so on and so forth. So that is what is the meaning of the term steady state. And whatever we'll study in the process of heat conduction will be assuming that steady state has been achieved. Okay, let's move further. Let's say we focus our attention on a particular cross section. Let us say we are looking at this particular part of the rod. So I'll draw that part over here. Let us call this 1 and 2. So this is 1 and 2. And let us say this is at temperature θ1 and this is at temperature θ2. We are assuming that steady state has been reached. So this temperatures θ1 and θ2 is going to remain constant. Let us say the length of the rod is A, and let us say the cross section area, right? If it is a circular cross section, let us say this cross section is A, and of course this cross section is also A. In steady state, what happens is, if this is taking heat Q by T, if the rate of heat transfer is equal to Q by T, if I denote it by Q by T, then all cross sections will have the same rate of heat transfer. If this absorbs 10 joules in 1 second, all the sections will absorb 10 joules per 1 second, because we have achieved steady state, because the entire heat that is coming over here is getting passed on. There's no losses. So rate of heat transfer remains constant. So if Q by T is the amount of heat which is absorbed by this surface in T seconds, this will also absorb Q by T, or Q joules in T seconds. So rate of heat transfer is constant throughout. Okay. The other thing is that this Q by T, the rate of heat transfer, depends upon a number of factors. It is proportional to cross-sectional area A. Larger the cross-sectional area, the rate of heat transfer is more. It depends upon the temperature difference θ1 minus θ2, the temperature difference. And θ1 minus θ2, θ1 of course will be lesser, θ1 will be larger, θ2 will be smaller. So the temperature gradient of θ1 minus θ2, it depends upon the temperature gradient. If the gradient is more, heat will transfer faster and is inversely proportional to 1 upon length. That means if you have a longer length, the rate of heat transfer decreases. And I think this is quite easy to understand, right? The heat transfer depending upon cross-sectional area, depending upon temperature difference, and is inversely proportional to length. And therefore, if I put this in terms of an equation, I will get the equation Q by T is equal to some constant K into θ1 minus θ2 A upon L. So this is the equation that we get for the rate of heat transfer Q by T, where this constant K is known as the coefficient of thermal conductivity. And this depends upon the material. Different materials have different thermal conductivity. Larger the value of K, that means this particular rod is more conducting in nature. Okay, a few more points about this topic. θ1 minus θ2 upon L, this particular term. This is change in temperature per unit length. This is known as temperature gradient or thermal gradient. Okay. Let's look at the units of K. So K would be equal, if I make K the subject of the equation, it would be Q by T L by A and θ1 minus θ2. So this would be the formula for the coefficient of thermal conductivity, and the unit therefore would be Q would be joule, time would be second, this would be meter, this is meter square, area, this is length, and this is degrees Celsius. Meter cancels, so I'll get the unit of K as J per second per meter per degree Celsius. And if joule per second is watt, so I can also write the unit as watt meter per degree Celsius. Also you can write the unit as watt meter Kelvin minus 1, but I avoid using this unit because there's a possibility of getting confused between this K and this K. This is Kelvin, whereas this is the symbol for the coefficient of thermal conductivity. So generally we would use one of these units for the coefficient of thermal conductivity. Right, so we have looked at, I've just given you a brief introduction to how heat transfer occurs, and I've introduced to the term of thermal conductivity. And what is important in this case is to understand that the rate of heat transfer is proportional upon these factors, and we'll also need to clearly understand what do we mean by a steady state. As I said earlier, whenever we'll be studying conduction, we'll be looking at steady state, or we'll be assuming steady state, and then maybe using this particular equation for various situations. When I do the next video, we will look at a composite rod. A composite rod is one in which the rod consists of two different materials, and therefore their conductivity would be different, and how that affects heat transfer. And that is a point, that's a subject of discussion for the next video. Thank you.